based on like some really, not really old, but relatively old mathematics. Then also on a paper by Simon Kernhout, but I will not be talking about his paper. I'll just be discussing his results from different points of view. And on this paper with David Simons-Defin and some work in progress with David Simons-Defin, Sasha Zhabayadov, and Murat Kaloglu, which hopefully will come out soon. Well, one paper is going to come out on Monday, but it's not going to be this. Okay, so let me start with motivation, and I'll go, while talking about motivation, I'll go over different things that I'm going to talk about. Can you do something with the noise, or is it bothering anyone? I think it. Oh, okay, thanks. Right, so we all learn that in conformal field theory. Yes, so I'm going to be talking about conformal field theories. In conformal field theory, we all know that if we learn OPE data, then we can use it to compute 4-point functions and also higher point functions. So the OPE data consists of scaling dimensions of local operators and OPE coefficients. And here I'm using the following notation. So delta is a scaling dimension, depends on the spin of the operator. So far, spin is integer. And at each spin, there can be several operators. And these operators are going to be labeled by index I. And these operators are also labeled this way, O, I, J. So if you know these things, you can use conformal block expansion to go to, say, 4-point function of phis. For simplicity, let's think that phi is some just scalar. And a lot of what I'm going to be talking about today is going in the other direction. And so it's probably a bit less known, but it's been figured out like 40 years ago by people who are doing harmonic analysis. And I wouldn't be talking about this if there were not some new developments. In particular, one new development is that Simon Kernhout derived a formula which allows you to go from 4-point function to the OPE data. And this formula has lots of nice features. This formula is analogous to Forsad-Gribov inversion formula in S-matrix theory. And then feature which is going to be most important for this talk is that this formula is analytic in spin. So you can write an integral of 4-point function which gives you this information, and this integral depends on parameter j, and you can see that everything in this integral is an analytic function of j, so it produces for you some analytic continuation of this data. And so usually we talk about local operators as integer spin, and now we have some analytic continuation. And one question that I want to address is what this analytic continuation is good for. So before I'll go into that, I will discuss in more detail this Lorentz inversion formula, which is what Simon derived. But before that, I will also cover Euclidean version of it, which is something which was known for a while. But before I start going into the details, let me finish just like a brief overview. So one thing that why we're interested in studying this analytic continuation, one answer is that it's used, for example, in conformal registry theory. So let me briefly remind you what that is. In conformal field theory, we all know that there is operator product expansion and converges, and this is what allows us to compute 4-point functions using OPE data. And the precise statement is that if you take two local operators and you act on the vacuum state, then you can express this schematically as a sum over other local operators acting on the vacuum. And the sum is convergent. And this is really the statement about OPE convergence. It's not the statement, like if you remove vacuum state here, it's not true. And this statement works both in Lorentzian and Euclidean signature. And as I said, if you remove vacuum state, it's not going to work well. I mean, it maybe works asymptotically or something like this, but it definitely doesn't work as a convergent expansion. And one example is given by so-called Regge limit. So let's consider a 4-point function. And I'll just look at Weidmann 4-point function with ordering 04, 01, 02, 03. And the way I'm going to insert these operators in Minkowski space, I have some null sheets, and I'm going to put 1, 2, yes, 3 and 4. And I'm going to take the limit where all these points become highly boosted. And so you can see that in this causal configuration, 2 is time-like from 3, and 1 is time-like from 4, which means that you cannot use microcausality to commute O1 and O2 together to act on any of the vacuums. For example, you cannot move both of them to the left vacuum, because even though you can move 2 to the left vacuum, you cannot move 1 to the left vacuum, because 1 doesn't commute with 4. And the same is true for the right vacuum. And so you cannot use this statement for this 4-point function. And indeed, if you try to use OP between O1 and O2 here, so you write conformal block expansion, you figure out what does it mean to compute this Weidmann function, and you find that this conformal block expansion does not converge. But naively, you would expect that there is some nice OP, because if you ask what this means in terms of cross ratios, this is z bar going to 0, but after some analytic continuation. But so kinematically, it looks very nice. In particular, for example, 1 becomes light-like from 2 in this picture, and you might naively think that you should be able to do something, but this conformal block expansion doesn't work. And so conformal Regge theory is supposed to solve this problem. And to solve this problem, it uses an idea of analytically continuing OP data in spin. I'm not going to go into detail, but let me just say what is the result, assuming that there is such an analytic continuation, and Simon's formula, Lorentz inversion formula, provides precisely the analytic continuation that you need for conformal Regge theory to work. So if we plot our local operators in the plane d minus delta minus d/2 and j, then we will find something, for example, at spin 2. We're going to find stress tensor, and maybe then there are some other operators, higher spins, maybe some other operators here. The statement is that analytic continuation, if you connect these local operators by some continuous family, then you find picture of this sort. I'll explain in a second why this feature has to be symmetric in this variable. So physical operators only live to the right. This is just some continuation. You maybe have some other families. So the statement of conformal Regge theory is that if you find this intercept here, call it J0. So this is spin. J0 is somewhere below 2, let's say. And the statement of conformal Regge theory is then that this correlator is proportional to exchange of conformal block with dimension delta equals 1 minus J0. So you can make this more qualitative, or you can write a formula for what dominates this correlation function. But the important point is that I want to convey is that you can think that this correlation function is dominated by one conformal block with scalar dimension, which is fixed by this analytic continuation in spin. Spin of the conformal block is 1 minus d over 2. And okay, let me say this now, that so here at this point you have spin equals j naught, and it goes here, and you have dimension equal d over 2, and this is goes here. And I'll explain where this comes from later. So this conformal energy theory motivates the idea that maybe if the OP does not, if the usual local OP does not converge in non-vacuum states, well, that doesn't necessarily converge in non-vacuum states, maybe there is a statement of the form that you can still write this as a sum, maybe of which gets contributions from the local operators, but then also there are some other contributions of some new types of objects, which I'll denote in this way, which are in some sense analytic continuations of local operators in spin. Yes. Sorry, can you? Yeah, that's a very good question. So the positions of local operators are independent, and about trajectories, they're independent in perturbation theory, but more generally, we do not have a proof that they're independent. And okay, and so the idea is that probably there is some analytic continuation of local operators in spin, which gives you some new operators, and you have to include them alongside with local operators in the OP if you want to compute it in non-vacuum states. And now we don't know any formula of this form, but what I'll try to do in this talk is to define in general CFTs what these operators are, these new operators are, and try to talk about a different application, which is not the Regge theory, but it's related to operator product expansion of average null energy operators. And so let me explain what I mean by this. Let's take some null sheet in Minkowski space. So this is some coordinate x minus equal to 0. There's some transverse coordinate y. And what I want to do is I want to take a null line here parameterized by x plus and consider an integral dx plus t plus plus x minus equals 0 x plus and some transverse coordinate y. So this is an integral is from minus infinity to plus infinity, and this is usually called average null energy operator, and I'll sometimes just refer to it as ANIC operator, and the ANIC comes from average null energy condition, which says that this operator is non-negative. And the object that I want to study is when we insert two such operators at transverse position 1 and transverse position 2, and we study them as they approach each other. So why this is interesting is, I mean, first of all, some relatively simple observable, but another reason, like more physical reason why this is interesting is that by performing conformal transformation, if you put average null energy operator at future null infinity, so this is the integral over some null sheet. Future null infinity is an example of such a null sheet. You can perform the integral over future null infinity. This is the Penrose diagram of Minkowski space. Then you can interpret this operator as measuring the energy flux at infinity. So if you have some event here and there's some energy coming out, this operator measures the energy which goes in some particular direction. I'll explain this in more detail later. But the physical picture is that you imagine doing some experiment here, and then there is energy flying out, and you put some energy detector, like some calorimeter, far away in the direction, and you measure what is the energy accumulated there. And when you have two of them, you put two detectors in two different directions, and when you study this OP, this is like studying what is the correlation of energy when you make the distance very short between them, well, the angle very small. And Hoffman and Maldacena studied the energy detectors, just a single energy detector, and then they argued also that when you want to take OPE of energy detectors, of two energy detectors, then how should I say this? So if I define this operator to be some E of y, then Hoffman and Maldacena argued that E of y1, y2 have some OPE, which is dominated by some non-local operator. So it's not necessarily the same non-local operator is there, but it'll denote by the same letter, which has spin equals 3 in some definition of spin. And they discussed this picture more or less qualitatively, and the point that I want to make is that by studying connection of these guys to Lorentz inversion formula, developing some technology, you can actually write down a very precise OP expansion for these operators. You can show that they're the same operators that appear in the Rege theory, and you can actually perform calculations with this. So this is the rough outline for the talk, and are there any questions at this point? Okay, cool. So let me start with Euclidean inversion formula, and what I mean is that we have this idea that if you want to compute 4-point function, then we can take a sum over all spins and over all operators with that spin of squares of OP coefficients times the conformal blocks. So here, this is the 4-point function, squares of OP coefficients. This is conformal block with dimension delta I of j, spin j, and it has depends on the insertions of these 4 operators, x1 to x4. And we want to find the formula which, given the 4-point function, will reproduce this set of OP coefficients and scaling dimensions. If you think about this a bit, you can realize that this is not the good formula to invert, because I mean, on one hand you can say, well, okay, this is some function and I'm expanding it in some basis, but we actually don't even know in which basis we're expanding because we don't know these numbers. So it's not a nice expansion to invert, and instead it turns out that it's more natural to invert a different expansion, which is called conformal partial wave expansion. And this expansion you can obtain by studying harmonic analysis on conformal group, and this was done like in the 70s. So let me review this first. And then there is connection between these two expansions, and you can infer this information that you want from the conformal partial wave expansion. So harmonic analysis is the idea that if you have some group, you have objects which transform under this group, then you can take objects which transform in some complicated way, and you can decompose them into objects which transform in a simple way. In some sense, it's the same as taking some representation, decomposing it into reducible representations, but it's technically a bit more general, but you can just think about it in this way. So what is the complicated object that we want to decompose? Naively, you might think that we want to decompose the 4-point function into simpler objects, but 4-point function is already invariant under conformal group, so there is nothing to simplify from the point of view of action of conformal group. So the only option is to take a 4-point function and forget about some dependence of it on some coordinates. For example, you can take 4-point function just as a function of the first insertion and just forget about the other insertions. Then this is certainly not conformally invariant, but the single operator already transforms in the simplest possible way. It's irreducible, so there is nothing to do here. And because 4-point function is conformally invariant, the same is true therefore for 3 operators, because transforming 3 operators is the same as transforming 1 operator. And the only interesting option is to study transformation under two operators. So here you have some function of x1 and x2, and it transforms in some non-trivial way under conformal group. And if you apply a conformal transformation, it's not conformally invariant, so you can ask about decomposition of it into things which are simpler under conformal group. So I will draw a lot of pictures because the formulas can get clunky. So I can represent this by two-point function. So I would represent four-point function by something like this, but because I don't want to think about the other insertions, just about the first insertions, I omit these other two legs. And as I said, you can think about conformal, about harmonic analysis as taking something, decomposing into irreducible components. To decompose into irreducible components, you usually need Krabchuk coefficients, and if you reflect on this, Krabchuk coefficients are just nothing but invariants in invariant tensors in tensor product of three different representations. And here, irreducible representations are just single local operators. So by some reflection, you can conclude that Krabchuk coefficients for us should be the three-point functions. And indeed, if you do everything carefully and rigorously, what harmonic analysis instructs us to do is to compute the integral over x1 and x2 of some standard three-point function, which I will just denote in this way. Against this four-point function. And pictorially, we can represent this as this diagram. So here, this three-point function is not supposed to be something physical. It's just some standard expression that you can write down. It contains two scalars and one traceless symmetric operator in spin j. And here I have put a bunch of tildes. And what a tilde over an operator will denote in this talk is that you take its scaling dimension and you replace it by d minus delta. And the reason for this is that if you do this, then phi has dimension delta phi, let's say. Phi tilde has dimension d minus delta phi. So in total at point x1, you have dimension d. And if you add dimension of the integration measure, you get 0, and this makes the integral conformally invariant. And the whole reason why we want to compute this integral is that you can prove that there is a completeness relation to which says essentially that you can sum over spins, you take an integral over scaling dimension over an imaginary contour which takes the form that delta is d over 2 plus some real number plus some imperial imaginary number. And you also take an integral over, no, you start from d over 2. Yes, because the representations is plus and minus are equivalent, so you can take only half of the integral. I'll explain it. Yeah. Representation is delta and d minus delta are equivalent. The shadow transform is like an intertwiner between them. Well, okay, here I'm glossing over some subtleties, like if the representation is traceless symmetric, then yes. If it's not, then the shadow transform also does something, in general, does something to the spin. It applies a reflection. And right, so the integral is this. And the answer is just product of delta functions. This is the rough statement. There are a bunch of subtleties you can ask me about offline, but they're not conceptually very important. So just to clarify, here again we use, this is not a physical 3-point function, this is a standard 3-point function, just some conformally invariant expression. This is the same thing that we used in this integral, and we are integrating over this point, so we're contracting this 3-point function essentially, and then we're doing integral over delta in this contour in imaginary plane, in complex plane. And we are summing over all spins from 0 to infinity. So what does this mean is that we can write our 4-point function again as in the following form. So we write, I'll just draw a diagram. Let me not add these two legs just yet. So we can write this as sum over spin, integral over delta, and then we have diagram. So I just took this formula and contracted it with a 4-point function. And so it tells us why it's nice to take that integral above is because, so this part of the diagram is that integral on the blackboard. And if we compute this integral, we can then reconstruct the original correlator by taking an integral over deltas and j's. So how does this apply to 4-point function? In 4-point function, we have to add 2 more legs. So we draw them here. And let me study this object first. So there's some diagram of this form. And you can see that if you just look at it from the outside, it has only 3 legs. So it must be proportional to some conformally invariant 3-point tensor structure. So I can write this as some coefficient C delta J times standard conformally invariant expression for the quantum numbers that the external legs have. And then if I want to just extract the number of C delta J, what I can do is I can add another 3-point function here and do contraction like this. And the idea of doing this is just to remove the dependence on external coordinates, because this object is not physical, it only depends on standard 3-point functions, and it's just some number. So I can normalize everything that this number is 1, and so this just gives me C delta J. Now if we look at this diagram, then it has this outer part, which we are contracting as our 4-point function, which looks like this if you redraw it. And if you decode this diagram in terms of 3-point functions, you will find that this is what is usually called the shadow integral, and it is giving a function psi delta j 4 points, which is, it looks kind of like conformal block, but it's not a conformal block, it's a sum of conformal block plus its shadow, so delta tilde. This is again called d minus delta. And then this identity, if you rewrite this in terms of 4-point function, you'll find that it gives you c delta j as the following integral. So here, this is essentially the formula expression for this diagram. The only thing that is probably a bit different is that I put a tilde over psi, and this is to indicate that this conformal partial wave at external legs transforms a shadow function, like with shadow dimensions of phi, so that this integral is actually conformally invariant. And then if you use this in this upper formula, what you find is that, so you just replace this part of the diagram with c delta j times 3-point function, then you'll find that the 4-point function is given by integral over sum over j, integral over delta. C delta j times conformal partial wave, this time without tilde. Are there any questions about these expressions? In principle, you can think about this as saying that, okay, there is this complete set of wave functions psi, and I'm just decomposing 4-point function in this basis, and this is the inverse decomposition, like the inverse formula, and this is a valid approach to this. You can think of these functions as being the complete set of eigenfunctions for conformal Casimir. However, this derivation using 3-point functions is conceptually more general, and it will be, I mean, you can also rephrase it in terms of eigenfunctions for the Casimir, but it's a bit more general, and it will be important later in the talk. Now let me just say how this expansion conformal partial waves relates to conformal blocks. And the idea is that you use this relation that conformal partial wave is the sum of a block and shadow block. You get two terms here. Well, actually, first you can look at this expression. You can see that psi of delta is the same as psi of d minus delta, and from this you can conclude that c of delta j is the same as c of d minus delta j. Then by using this property and this identity for conformal partial wave in terms of conformal blocks, you can rewrite this integral as sum over j, integral from over d over to from minus I infinity over to plus I infinity d delta 2 pi I c delta j, and then conformal block instead of conformal partial wave. And the conclusion here is that the way to reconcile it with conformal block expansion is to require that in complex plane of delta, function c delta j. So the integral that we perform is over this line. And the way to get discrete sum is to require that the c delta j has a pole, has poles in the on the real axis at dimensions delta I of j, and that this OP coefficients f fi phi o I j squared are just minus residues at delta equal to delta I of j over this function c delta j. Then you can deform this contour to the right, you pick up the contributions of this pulse, and you reproduce the conformal block expansion. So, are there any questions about this relation? Great. So basically the lesson that I want to take out from this whole discussion is that there is this function c delta j, which conveniently encodes the OP data in position of its poles and their residues, and that you can do this contractions with 3-point functions to compute it. And one way to say this is that you can actually, given our understanding of the pole structure of this function now, you can actually you can actually schematically at least write this identity that if you want to compute, suppose you have some large correlation function with a lot of external legs, and one of the legs is you just isolate one of the legs and it's given by some local operator, then we can write this as minus residue at delta equals delta I of j of this integral where these two legs are just some two scalars phi. So in a sense, if you only had the correlation functions of operators phi, you could use this identity to reproduce correlation functions of other local operators. And you could even see in principle from this formula why these operators are local, because in the right-hand side you have some non-local integral, but you can argue that the poles in this integral actually come from the regime when the two phi's collide. And so these operators are local. Now, one question that you might ask is, why don't we just, if you want to get some analytic continuations, why don't we just analytically continue here? Because it's like there's j is some parameter in this 3-point function and doesn't enter here, and let's just do this. And the answer is that this 3-point function, you cannot define it for continuous spin. You cannot define it for a non-integer spin. I mean, you can define it, but it will necessarily have some branch cuts, and you wouldn't know how to do this integral. And in terms of the formula, with conformal partial, in terms of the formula that I just erased, where we computed c delta j as an integral 4-point function against conformal partial wave, the same is true. Conformal partial waves for non-integer j have branch cuts and Euclidean signature, and you cannot define them you cannot define c delta j using this non-integer spin. And this is where this Lorentz inversion formula comes in. And I will not derive it right now. I will derive it in a different way a bit later. Well, I will derive it in the same way as the Euclidean one, but I will not. But this requires some preparation. So let me just state what the formula says. It says that c delta j can be computed. So before, I should say I had all integrals for over Euclidean space. Now I have an integral over Lorentzian space, or Minkowski space. And so appropriately, we also have now Lorentz conformal group. And the integral is now not is the 4-point function, but rather is this double commutator expression. So it's just the vacuum expectation value of commutators of phi. And we're integrating now against not a 4-point function, but instead a conformal block of x1, x4. But this conformal block has funny quantum numbers. Instead of dimension, we have spin plus d minus 1, and instead of spin, we have dimension minus d plus 1, or d is dimensional space. So this is this funny combination of quantum numbers is somewhat reminiscent of the funny combination of quantum numbers that we had in the leading contribution to our edge limit, and we will see why these two things appear quite soon. But just generally, this is a concrete formula. There is like some prefactor here in terms of gamma functions. And it has various nice features. For example, if you try to expand this 4-point function under the integral in a different channel, then there is a sense in which it's simpler because these double commutators kill contribution of double trace operators, double trace operators built out of phi. But for this talk, what is most important is that this function is actually analytic in J, because here I have some explicit gamma functions, which of course can be analytically continued. And the only other place where J enters is in the dimension argument of the conformal block. And conformal blocks are obviously analytic functions in dimension. This is well known. What is actually less obvious from this formula is why C delta J is analytic in delta, because now delta enters into the spin argument. But if you think about this carefully, you can show that conformal blocks are actually well defined for non-integer spin for the causal configuration that for which this double commutator does not vanish. So in the integration region in this formula, this is completely well defined for non-integer J and delta. And so in principle, you can just say, okay, now I have C delta J defined for like all delta and J, and I have an analytic continuation of all the OP data. It's a bit more subtle than that because this integral only converges for real part of spin greater than J naught, and for delta on principal series. So this values where real part of delta is d over 2. They're called principal series, and for these values of parameters, this formula converges. Of course, if you know some analytic function in this region, you can then take an analytically continuous C delta J to other values. Yes, sir. Yes. It's true. Yeah, it's true for all conformal blocks, but it's easiest probably to see in 4 dimensions. 4 dimensions, you have like this k functions, and there is a product of 2 k functions. One is delta plus j, and another is k of delta minus 2 minus j. So here you can see that, and this is for the usual conformal block, delta j. So here you can see that this conformal block is invariant under j goes to minus 2 minus j. And because here dimension is in this slot, then this turns into this identity. Yes. Okay. Right. So what I was saying is that if you, this formula defines C delta J in this region of parameters, and then you can define this analytic continuation. From there, it's uniquely defined, but it's harder to learn about its properties. For example, in the case of integer J, we know that C delta J must be a meromorphic function with poles which are with simple poles, and the residues are related to local operators, and we don't necessarily know this for C delta J for non-integer J. And I think this is a very interesting open question to study this more rigorously and prove maybe some statements about it. You can show that in perturbation theory this is true. Well, C delta J is meromorphic for all J. It's not simple poles, it has higher order poles which encode anomalous dimensions. but it is still meromorphic, and you can define like well-defined delta ij at an integer j and so on. But non-perturbatively, I don't think anything is known. And for the purposes of this talk, I will assume that C delta j is meromorphic. For all j. But that's not strictly necessary for all that I say to make sense. You can say extra words and make sense of the formulas that I'm going to write without this, but it's just going to be really complicated, so let's just assume this, and if somebody proves that someday that it's not meromorphic, then we can modify the discussion. But it's useful to keep in mind that not much is known about this like rigorous analytic structure of this function at complex J. Okay. So what I want to do now is to try to explain how to lift this function. So we had a similar formula in Euclidean signature where there was not a double commutator, but just the Euclidean correlation function integrated against conformal partial wave. And for that case, we have a formula of this form where we can say that we essentially can define local operators by residues of this integral. What I want to have is a similar formula for the Lorentzian case. This Lorentzian inversion formula, I want to have an analytic continuation of this in spin, and to claim that this gives an analytic continuation of local operators in spin. But before even writing something like this, I need to explain what does it mean to have an operator with non-integer spin. So let us change discussion for a second and just talk about, in general, how can we talk about operators with non-integer spin, what properties they must have, and so on. So usually, let me focus for simplicity on traceless symmetric operators. And a traceless symmetric operator with integer spin j is a function of x, which carries j indices mu1 to j. It's symmetric in this indices, and it's traceless. And we want to somehow generalize this description to non-integer spin j. It of course doesn't make sense to generalize the number of indices to non-integer value, because that must be integer. So we first need to write this a bit differently, and we pass from this operator to a function of x and the polarization vector z, which is defined to be just a contraction of z mu1, z mu j, with a local operator. Now, if you allow z to be any vector, then this obviously encodes all the information that we need about this tensor O mu1 mu j, because by definition it's symmetric in this indices, and we can just reconstruct this tensor by taking derivatives with respect to z. However, there is a more refined statement which relies on the fact that this operator is also traceless in this indices. And the statement is that it suffices to consider null vectors z, and it also suffices to consider null vectors z which live in the forward null cone. And then this function will still completely encode all the information about this traceless symmetric tensor. And you can actually reconstruct this traceless symmetric tensor by taking appropriate derivatives with respect to z, just that now these derivatives have to be more complicated because z is constrained to lie on the null cone, so there's some derivatives on the null cone. But this can be done. And so in this way, we can encode this operator in terms of function OXZ, which has the following properties. It's homogeneous in Z. And in appropriate sense, it is polynomial in Z. So roughly speaking, you can think of this as just saying that O of xz has this expression, but there is a more intrinsic way of defining this. I just don't want to spend time on it. And then the statement is that if you have a function with these two properties, then you can uniquely reconstruct from it this trace-semantic operator and vice versa. And now it's clear that in this description, it's very easy to generalize the first property to an integer spin j, because if we constrain z to lie in future null cone, lambda can be only positive, and then if lambda is positive, then we can, of course, replace j by any complex number, and it's completely well-defined property. However, this second property, that it's polynomial on z, we cannot generalize. And the solution is just to drop this property completely. And I should say that this is completely motivated by representation theory. And if you ask, Lorentz group has well-defined representations with non-integer spin, and this is how you construct them. So you can land on this definition just by doing standard representation theory analysis. I just don't want to go into this, but this, like, dropping this requirement is the correct thing to do. You should think of this as a shortening condition which is only possible for integer j. For an integer j, it's not possible. It's not Lorentz invariant to impose this. Yes, but a set of finite dimensional representation. This is not a finite dimensional representation. Yeah, the infinite dimensional representations are very different for depending on the real form. In particular, like, if you take compact real form, then I think all sufficiently nice infinite dimensional representations just decompose into direct sums of finite dimensional ones. Whereas if you have some non-compact directions, as in Lorentzian conforming group, then you get genuinely genuinely infinite dimensional representations which are reducible. Okay, so this is the thing that we want to study, and to distinguish such operators which are defined for which have some continuous j, I will use this notation again. And for now, let us just imagine that we have a conformal theory. It has such objects, and what properties do such objects have? But let's just assume that we already have such things, and what do we expect from them? So the simplest thing that you can do if you have an operator, so we have this operator like z, and I will explicitly label it by spin j. We can act with this operator in the vacuum state. And we can ask, so we get some new state psi, which has spin j in some sense, and we can ask what is this state. If you're being more pedantical, you know that this is not, like, doing this does not make sense even with local operators, because this state will not be finite norm. And then if you really want to, you can smear this with some test function, maybe both in x and z. And then this will give you a finite norm state. Well, we don't know whether it's going to give us a finite norm state with this weird object, but let's imagine that there is a way to make this finite norm in well-defined state. So the main claim is that for j which is non-integer, which is not a non-negative integer, this state psi j must vanish. It must be 0. And there are many ways to see this. I guess that there are two different arguments. One argument relies on the idea of positivity of energy. The statement is that if j is non-integer, you can prove that this state has components with arbitrarily, like roughly speaking, has overlaps with states with arbitrarily negative energy. just from representation theory. And the other argument is that in conformal group there is a set of conformal Casimirs. For example, there is a quadratic Casimir, choroidic Casimir, and so on. Depending on what is the rank of conformal group, we have some finite number of Casimirs. And we know the and these Casimir operators, there are just some Hermitian operators in the Hilbert space, and they have a discrete spectrum. And we know what the discrete spectrum is. It's just given by the Casimir eigenvalues corresponding to each primary operator, local primary operator in our theory. And this just follows from operator state correspondence. So this set of operators, they have eigenvalues which form some discrete set. And if we now imagine that there is some continuous family of operators Oj, where we can vary j continuously, we can compute the Casimir eigenvalue of state psi, because it's just created by this operator O, and if we assume that operator O is primary, which is natural because we want to analytically continue primary operators, then you can just write down the formula for its eigenvalues. For Casimir eigenvalues, you will see that this eigenvalues vary continuously with spin j, and so most of the time they will not lie in the spectrum of Casimirs in Hilbert space, and so the states must vanish generically. So there are lots of ways to see why such states would be bad if they were non-zero, and so the claim is that such operators from an integer spin must necessarily annihilate the vacuum state. But this leads to a problem, because we know that local operators do not annihilate the vacuum state. So if you have some local operator, you activate it on vacuum, we definitely get non-zero, because there is a theorem which says that if you have a local operator which kills the vacuum, then this local operator is vanishes by itself at zero. It annihilates all states. And so there is some tension, because naively we would like to say that there is some family of these operators labeled also by I and j, which is defined for any value of j, and for j, which is a negative integer, these operators reduce to local operators. And also there is a sense in which this family is analytic. So this obviously cannot be true now, because we know that generically this family must annihilate the vacuum. So if it's analytic, it must always annihilate the vacuum. But if it's a discrete points is equal to local operators, it cannot annihilate the vacuum at these discrete points. So there is a contradiction, and so everything fails. So we can go home. Fortunately, there is a solution which says that, and the solution is that to relax this condition a little bit and to allow there to be some transformation that you apply to a local operator before setting this equality. So the statement is that these operators will analytically continue not the local operator themselves, but rather some, say, integrals of these local operators, or some other kind of transform of the local operator, such that this transform has the property that actually if you apply it to local operator and act in vacuum, then you get zero. And if you want to require both these guys to be primary and these guys to be primary, and also we would naturally require this operation to be linear, then we find that this L should be some linear conformally invariant map between primary operators. And such things have been studied in mathematics. And people have found, classified them in various signatures. So in Euclidean signature, the only such thing is for generic values of scalar dimensions, the only such transformation is a shadow transform, which is not going to work here. But in Lorentzian signature, there are much more such transformations. They're called, in general, such transformations are called Knapp-Stein intertwining operators. And there is 7 non-trivial integral transforms, 7 non-trivial transforms to choose from in Lorentz signature. And you can go through the list and you can actually find that one has all the nice properties that you would want. So let me explain what is the candidate for this transform L. Are there any questions about this argument? Why there is a problem? Okay. So the definition of this transform, and it's really just fixed by conformal symmetry up to discrete choice, is that if you want to apply this transform to an operator O and evaluate this transform at parameters x and z, then what we should do is we need to compute an integral from minus infinity to plus infinity over some parameter d alpha with some weight minus alpha to power minus delta minus j, where delta and j are the quantum numbers of this local operator. It doesn't have to be local, but quantum numbers of this primary operator. And the thing that we're integrating is this operator inserted at point x minus z over alpha in this polarization z. So the claim is that after you do this integral, you get something which transforms like a primary, and the quantum numbers of this guy are delta L equal, I'll denote them by delta L, and they're equal to 1 minus j, and JL equal to 1 minus delta. You can immediately see that this is probably in the right direction because this is also the quantum numbers which appeared in, like this is also the combination which appeared in conformal Regge theory. And let me explain in more detail what happens with this integral, because there is some apparent problems here. For example, when you start integrating at minus infinity, everything is fine. This weight is positive, so you can put this to this power. This correction is also small, but then alpha at some point goes to 0, and everything goes to hell. Like something happens here, this goes to infinity. So what do we do with this? So the way to think about this integral is as follows. Let me draw a Penrose diagram from Minkowski space. To the best of my ability. So we have point x where we want to insert this L of O, and we have some null vector z which we want to use as polarization. Then the integral instructs us to start at alpha equals minus infinity, in which case O is just inserted at x and z. Then as we increase alpha, this point starts moving in the direction of this null vector z. So it continues until it hits the future null infinity, and this happens at alpha equals 0 here. And then to explain what happens to the integral next, you need to remember that in conformal field theory, correction functions of any conformal field theory can be analytically continued from Minkowski space to Lorentzian cylinder. So you can always think about Minkowski space as being just a Poincare patch on R times z minus 1. So roughly speaking, Poincare patch on the boundary of ADS. There is a well-defined analytic continuation of all correlation functions, and this means that you can continue this integral actually out of this Poincare patch, out from the Minkowski space to the next Poincare patch, and then you just end at the point x plus at alpha equals plus infinity, where x plus is just the point. It's a well-defined image point for x, and the way you construct it on Lorentzian cylinder is you take point x, you send light rays in all possible directions, and after time pi they will converge at point x plus. So it doesn't matter if you take some other light ray, it will also come to the same point. So it doesn't. This point x plus does not depend on the direction of z, and the relation between x and x plus is conformally invariant. So this is the integration contour that you must use in this integral. And then it turns out that the way you analytically continue correlation functions, it takes care of this undefined phase in positive alpha. And so this is perfectly well defined, and you can show that it converges for, and it's kind of obvious from the definition. For delta plus j greater than 1. So you can apply it to most local operators. Say in 4 dimensions, you can, in unitary theories, you can apply it to all local operators. And in 3 dimensions, you can apply it to everything except possibly for some scalars of low dimension. And I will refer in what follows to this transform as a light transform, which is opposed to shadow transform. And this is because you integrate over a light ray. And the claim is that indeed you can check that this is true. That if you take a local operator, you compute this integral, act on vacuum, you get 0. And the way to see this is that this is still some integral of the local operator. So the only states with which it can have non-zero overlap are those created by the same operator O. And you can just take this 2-point function, you can evaluate the integral, and you can see that it's equal to 0, provided that it converges, of course. Yeah. No, Z is real because we're in Minkowski space. Z is a real null vector for future point. Yeah, this is important because that's why I cannot do this in Euclidean signature, because in Euclidean signature we would have to use complex Z. Sorry? Yes. Yes, if you put both delta and j in principal series, then this is equivalence representation. In physical theories, it's not equivalence because it's, I mean, for example, when you act on vacuum, with O in vacuum, then O creates sort of its Fermat module, but L of O gives 0, so it's obviously not an equivalence. But if you were to work with principal series representations, then it would be an equivalence, yes. Yeah, this is what's called Knapp-Stein intertwining operator. I think it gives an equivalence in these cases, yes. Okay, so the conjecture now is that you can form analytic families of operators which will satisfy this condition that they are parameterized by some number j, and the integer j they reduce to light transforms of local operators. I should say that immediately that this is now a bit misleading because these operators Oj do not have spin j anymore, because the local operators with spin j, the spin j goes to dimension of this guy and not to the spin because of this transformation. But since the dimension goes into spin, they still have non-integer spin in general. Yeah. Yeah, it would just have like an integral over this line. The weight would be just sine, like you would be integrating over something from 0 to pi, and the weight would be sine of. Yeah. Helix. Yeah, exactly. You just move time pi, and you stop after time pi. Well, the point is that. Well, okay, so it does not excite the vacuum, and let me give you sort of, let me say some words which might help, and if they don't help, let me know, and I'll try to say something else. So one example of this light transform, which we are actually very familiar with, is that, let me write it here. So one thing that we can do is we can take this point x and we could push it to past null infinity. In that case, we'll just have a integral which starts at past null infinity and ends on future null infinity. And the formula for it, after you figure out the conformal transformations, is that so you can parameterize the points at past null infinity in this way. So you take, so you basically take vector z and you push x in the direction opposite to vector z and until you hit past null infinity. So it's x is like minus infinity times z, and polarization vector is still z. Then this integral is given by this formula, and if you set z, for example, such that z plus is equal to 1 and z minus is equal to 0 and everything else is also 0, then this is equal to integral over dx plus minus infinity to plus infinity o plus plus plus, if it's an integer spin operator originally, of x. So for example, if you apply this to stress tensor, you get average Navier operator. And for average Navier operator, there is, you should really think this is not creating states, but rather measuring some fluxes. So average Navier operator, if you further push this to future null infinity, it measures the energy flux. And so roughly speaking, if you try to measure energy flux in a vacuum, you always get 0. Like yeah. Okay, so then phi, like, yeah, it doesn't. Okay, the best interpretation that I have for these operators is that you should think about them as detecting something. So for example, if you take, let's say it's like free theory or generalized free theory, and you take scalar which is phi squared, then this will detect the particle number at infinity. If you put it, I mean, the simplest physical interpretation is when you put it at future null infinity, but then everything else is a conformal transformation of this. You can prove that it doesn't create states. I'm not sure. If it's a detector, you wouldn't expect it necessarily to create states. And so the best intuition I have is that you should think about them as counting things which fly out. But I don't have any other picture. Maybe you can interpret this in some different way if you apply this transform to time-ordered correlation functions. So here it's important that you apply it to Whiteman correlation function, because in time-ordered, when you do this integral, it will necessarily cross some null cones, and then you cannot interpret this operator as acting in a vacuum, and maybe then it will have a different interpretation. But I cannot say anything about this. Okay, and now that we have this proposal, we can actually really easily, it's very easy to write down an expression for this O of j, for these new guys. And to do this, we can just start from, schematically, we can just start from this identity that I was writing before. That insertion of a local operator is minus residue of over in delta of this diagram. And here, so this identity is Euclidean, so this diagram involves some integrals which are over Euclidean space. So then you can do two simple things. First of all, we can recreate these integrals to make this Lorentzian, to make this integral over Lorentzian space, so this identity still holds. But then you can apply light transform on both sides, and this also continues to hold. And so you kind of insert light transform on this line. And but then, after you've done these two simple things, you can stare at this and you can realize that now the right-hand side has analytic continuation in J. Now, like all the issues which were problematic with making J an integer because of branch cuts, they're all gone. And the role that this slide transform plays here is because it annihilates vacuum in certain configurations. It cuts, like it reduces the integration region here. Because you're integrating here with some 3-point function. Configuration is such that both phi's, say, are like somewhere far in the future of this operator O of the slag. Then when you take light transform, this will give 0 because the slag is acting in a vacuum. So to remove some integration part of the integration region, and after that, the analytic continuation in J is possible. But this is just some analytic continuation. It's not guaranteed to be related to anything. But then you can show that if you restrict to 4-point functions here, then if you look at this integral, you can see that this integral is equivalent to, you can do some contour deformations, which are relatively simple, and you can see that this is equal to, you can replace the 4-point function by its double discontinuity, where double discontinuity is this double commutator that appears in Lorentz inversion formula. And now when you have this identity that, like this thing, like you have a double discontinuity, you take some integral, you get something which on the outside looks like a 3-point function. You can repeat precisely the same procedure that we had in Euclidean case. So contract this with another 3-point function and separate this as double discontinuity integrated against some other object. You will find that this object gives precisely the conformal block that appears in Lorentz inversion formula. And therefore, the analytic continuation that you get from this equation is the same as in Lorentz inversion formula. So you can view this procedure as like lifting Lorentz inversion formula to the operator level. However, if you really want to think about these things as operators, you have to prove this things that Shinano was asking about, is that whether this analytic continuation is the same no matter what, say, you can use phi and phi here, but maybe you can use some other operators and it will give different results. And so you have to study this, and the answer in general is not known. Formula still, of course, makes sense, but so far we have not proven that you can forget about what operators you used here. I think that you can forget. I mean, you can definitely do, like in perturbation theory, you can see, and I'll just say it now, that you can apply this procedure, say, to you can apply this procedure to like in free theories, and then in perturbation theory. So in free theories, what you get, for example, is that these operators OJ, they have schematic form. If you insert them at Pascal infinity, that they're like these well-known expressions how to construct operators with non-integer spin. Something like this, where S and T and are coordinates on along some null direction. So it's like in gauge theories, people insert Wilson lines. So I don't know about the Wilson line case, but if you just apply it to free theories, then you get integrals of this kind, which are something people have considered before, and then you can do perturbation theory just for these operators. Yeah. Yeah, but the important point is that you can write an operator, even if there is a mixture. This is still mixture between operators, not between 4-point functions. Yeah, there can be degeneracies, but it's still degeneracies between operators. And these operators, it doesn't matter in which correlation function you insert them. This is true in free theory, but in, say, if you do this in mean field theory, then it will not be true. There will be more parodies per spin, and you can write a formula which takes this into account. Yeah, that. Yeah, that. Yeah, yeah, yeah. We don't know. Like some conjecture is that just at integer speed, at non-integer spin, the C delta J actually has cuts, which at integer spin resolves into poles, and just the number of poles increases as you increase J. So that at generic J you have a cut. It's only at integer J it resolves into poles. That's one scenario. Yeah. Another scenario is just that it could also be that you have these trajectories, but at integer spin, some of them start getting vanishing residues. This is also possible. Yeah. Yeah, it's the same. I mean, you have to stare at this integral. It probes various regions and this. Oh, this is like the right-hand side defines left-hand side. Oh no, this yeah, I don't know. This thing makes sense at least formally for any J. But I mean, like this Lorentz inversion formula is a way to compute C delta J, and which converts just for some J. It doesn't mean that C delta J doesn't have analytic continuation beyond that regime. It's just you cannot use the formula to compute it, right? Because in free theory, these rigid trajectories are just straight lines, and you can continue them arbitrarily far below. Okay, let me try to explain in the remaining time how this is related to what I promised about operator product expansions for this energy detectors. Right, I should say that this derivation of like from here you can actually obtain Lorentz inversion formula for any like any quantum numbers of external operators, and you get a very beautiful formula which only involves like things like light transforms and some other natural objects, and it doesn't have like any factors of gamma functions or anything. It's like very beautiful. It fits in one line. I just don't want to spend time on to explain the notation. Okay. So, as I said, there you can think of this null integral of stress tensor that I was discussing in the beginning. You can think of this as the light transform of stress tensor operator, and then it makes it into this interpretation shows you that the average null integer operator is a primary, and primary it has dimension which is given by 1 minus spin of stress tensor, which is 1 minus 2, dimension minus 1, and has spin, which is 1 minus dimension of stress tensor, which is d, so it's a spin 1 minus d. From here, as I explained there, on this blackboard, if you want to go to the picture where you have a null integral over a null sheet, then what you do is you send x to past null infinity. But if you want to interpret this as a detector placed at future null infinity, then you set x to spatial infinity. So this is point x, and this is spatial infinity. So if you set x to spatial infinity, you'll have an integral in future null infinity, and you will effectively have a detector. So for detector interpretation, you want to consider stress tensor, like light transform stress tensor inserted at spatial infinity, And then you can replace also z by a vector which has time component equal to 1, and spatial components are given by some unit vector n. You can define this to be E of n, and then interpretation for this object is literally that you have some sort of event happening, there is some stuff flying out, and you put some sort of, I don't know, colorimeter here, and this direction is given by vector n. And you're just measuring all the energy which goes in that spatial direction. So the question that we want to address is, how do we study expectation values of products of these energy detectors? That is, we have now two detectors at one position and 1, another at position and 2, and they're detecting the energy which goes in these two directions, and we're bringing them. Now I want to discuss what happens when you bring it close together. So it's instructive to rewrite this product back in terms of these light transforms. So in terms of the slide transforms, this product becomes L of t at infinity with some polarization vector z1, L of t at infinity with some polarization vector z2. So now if I want to generalize to, I mean, it's more conformally invariant to not necessarily put everything in infinity, but it's important that this is the same point. So more generally, I can look at this product. I have two light transforms, they're both inserted at the same x, but at different polarizations. And normally, if these were local operators, you could complain that you cannot insert two local operators on top of each other. And here it's not obvious whether you can do this. Whether these integrals will converge, because if this is point x, then you have two null lines and you're integrating stress tensor. So along them, and there is a regime where stress tensors come close to each other. Then there is actually another regime when one stress tensor is here, but the other is on the other side, like this x plus. And this is a Reggie regime, and there is like light cone regimes, and there are lots of ways for this to diverge. But you can study all these questions, and you can find that in non-perturbative CFT, this converges. This is always makes sense. And say in large n, it also makes sense at tree level. At higher orders than 1 over n, this can diverge in large n expansion, depending on the theory that you're studying. So I'll just assume that this is well defined, which is said is a case in general CFTs. But then, because we put these two operators at the same point, it offers a lot of simplifications. For example, when you do this, you know that you have to just add the scaling dimensions. So the scaling dimension of this product is just twice times the scaling dimension of light transform of stress tensor, which is minus 2. But now I want to claim that there is a sum, that you can write this as a sum over these guys that we defined. And this information immediately tells us what are the scaling dimensions of what are the numbers j which appear on the right-hand side. Because if you remember, scaling dimension of this guy is 1 minus j. So we find that 1 minus j must be minus 2. So j is restricted to be spin 3. And this is sort of a more, this is the same as what was found by Hoffman-Maldacena, but working in a different frame where everything is placed on null sheet, and then this is counting some eigenvalue of some boost operator. Another point is that if you now act on, yeah, it's exactly the same argument, just in different frame. Another point is that since they're at the same x, if you act by a special conformal transformation which preserves x, since both are primary operators, this thing gets annihilated by the special conformal transformations. Therefore, the same as for all guys here. In the right-hand side, you can only get primary operators. You will not get descendants in x, but you can get descendants in z. So potentially, you could have here derivatives with respect to x, but you do not get them because here everything at the same point. I'm out of time, so I don't really have time to explain why. I don't really have time to explain how you can show that this is true, but you can actually show that, like, so far I was just saying that we should get the same operators here, but you can actually show that this is the case. And the rough idea, let me just say this in words, is that when you look at this expectation value where, say, psi is created by a local operator, then the way this looks like is that you have these two legs associated with psi, and you have these two legs associated with original energy operators. But these two legs, they're parameterized by these vectors n1 and n2. So n1 and n2, they live in d-2 dimensional sphere on the celestial sphere. Conformal group, Lorentz group acts as a conformal group on the sphere. And so from the point of view of n1 and n2, you just have some non-conformally invariant two-point function on celestial sphere. And there is an action of conformal group in the sphere. And this conformal group is just the Lorentz group of the full theory. And then you can do precisely the same exercise that we were doing in the beginning of this talk, where you perform harmonic analysis with respect to these 2 points. And you can define things which appear. You can find things which appear in this OPE by contracting with a 3-point function on the celestial sphere. So this is d-2 dimensional. And so after you do this, as an output, you get a single polarization vector. We didn't do anything to the coordinates x, so this whole thing is still at a single point x. So after doing this external leg actually does look like a single primary operator, which you can write on the right-hand side. And from harmonic analysis, it just follows that the things that you construct in this way is the things that you should write on the right-hand side. And then the argument is that you can show that the things that you get in this way are just precisely, again, the same operators. And the way you see it is by observing that you can replace this by double discontinuity. And this time it's completely obvious because suppose you have here a vacuum state and you add some external operator O3, O4, which creates the state psi, and then because light transforms annihilate the vacuum state, you can replace this by a commutator. And if you have some incoming state, then you can also replace it with the commutator there. So you immediately get that this is double discontinuity, and this is some operation that you do to double discontinuity to get a 3-point function, and then you can repeat the same procedure there, and you can find that it reduces again to Lorentz inversion formula. So these objects that you get here are precisely this, precisely the output of Lorentz inversion formula for spin j equals 3. And then you can of course do this for various things. You don't have to put stress tensors here. So a simple setup where you can do very explicit calculations is that you can work out the technology when these operators are scalars and external operators are also scalars. And in n equals 4, by supersymmetry, you can relate energy-energy correlator in stress tensor state to some scalar-scalar correlator in scalar state. You can use this technology, some knowledge of the OP data and its analytic continuation in n equals 4 to compute various expansions for this energy-energy correlators, and they agree with known results when such results exist. So I'll just stop here. Yeah, I'll just stop here. Right, right. So